Oh, and of course the arrangement of the icons is once more different. Bill Gates, you made a lot of people happy and a lot of people slightly ticked off. And if you can do that and become a billionaire, I suppose must have kept a majority of people happy along the way. Let's not get too philosophical. Let's not get Bill mad at us. All right. We are talking about CFGs, context-free grammars. Real quick recap, what do we need? We need a for tuple in order to define the context-free grammar. We need some non-terminals or variables. We need terminals. We need some rules. And we need a start on terminal. And with those four elements, we can define more robust, more complex patterns than what we could do using just regular expressions. Thinking back, regular expressions, let's think, what are those made up of? Regular expressions, you could union, or say, here, either take this or this. You could concatenate, say, take one from this collection and something from this other collection, put them next to each other. It was concatenating. And then you could star them, saying take 0 or more repetitions of whatever is in the parentheses. Well, those worked pretty good, but you couldn't do stuff like what? 0 to the n, 1 to the n, for example. And there are certainly limitations to what you can do with context-free languages, but a drawing a Venn diagram to keep in mind. Regular languages are a subset of the context-free languages. And we showed last time how you could do repetition. Notice that while a state in a DFA can have a loop on 0, say, the way repetition gets done in a context-free grammar has something to do with like a rule like B goes to or epsilon. So for shorthand, it is most common that you will write rules like this. So this actually would be most precisely 2 different rules for the non-terminal B. Remember that non-terminals, we use capital letters. Terminals are usually just for convenience. They're either symbols, parentheses, we can use any kind of symbols, but generally lower case if they're letters for the terminals. So rules take the form of a single non-terminal, We can interchangeably say a non-terminal is the same as a variable in that the rules are actually often referred to as rewrite rules because they're a replacement they say wherever you see a capital B, you can replace it with a either. This vertical bar is the or. Two different rules. One rule is B can be replaced with a 0 followed by a B. This is a recursive repetition. Or B can be replaced by an empty string, simply removing it from the string that has been developed. We said CFGs generate strings. See, mine should be good. CFGs don't really accept strings in the same sense that we think of a DFA would accept or reject a string. A CFG allows us to generate strings and derive them. So let's see. We would, if this were our entire grammar, we'd have a single non-terminal B. Our terminal would be just one of them, a 0. The empty string would be in the language. And I could generate W such that W is in the closure of the set 0, meaning as many zeros as I want, including none of them. And that would be, is that a regular language? I guess a good question is, could it be a regular language? If I use a CFG to define it, and I just told you this is what it means, that looks awfully like what? Well, that, right? So indeed, yes, this is regular. And because of this, indeed, it is also a context-free language. And I can represent it with a CFG, a context-free grammar. Okay. Any questions at this point? Kind of been walking our way through, hitting the high points since last time. Or not since, from last time, I should say. All right, and we'll press on. Again, I urge you to be reading in the text the parts that I'm covering here in particular. We will not do if I don't bring it up in class, then we'll not talk about it. So Chomsky normal form, I usually hold off if I do cover it. That's in section definition 2.8, page 109. depending on where we get, I make a determination whether to include that. It is a way to put a context-free grammar into a standard format, but recently I have not covered it. Well, last semester I did not cover it. I will put it in after the fact, after we get through push-down automata first. So we'll start with, there is an important add-on, or I'm going to put it, there's an additional perspective on how to create a push-down automaton from a context-free grammar. So we're going to look at the hard way, and then we're going to look at the easy way, and it actually makes the creation of push-down automata much more simple. And that'll become more clear as we go here a little ways. But let's look at a few examples of some context-free grammars and the languages associated with them. Okay. And in particular, let's look at the standard way of generating mathematical expressions. Okay. So a very common use of CFGs when you get into coming up with a grammar for a programming language such as C or C++, Java, Python has a CFG. What you pretty much have to deal with is mathematical expressions. Your book kind of dances around these a little bit. We'll look in detail. I'm looking for the page. Hang with me just a moment. So, hopefully what you can see here is that we can generate from a good math expression CFG, we can generate good, well-formed mathematical expressions. Let's start with an expression goes to expression plus a term, or just a term by itself. So normally when we talk about a mathematical expression, let's say a here's a little brief, simple mathematical expression. The normal way that we refer to the elements of this, things that are added together we usually refer to as terms, right? So if you have a sequence such as this, in between the plus signs, and if we're, I'm leaving out minus for a moment because it's exactly equivalent as far as our interpretation to the plus and the minus fall in the same place, the addition subtraction operators versus the multiply and divide operators. So we're just looking at the add and the multiply for simplicity. But the things joined by pluses here are terms. And factors multiply. Terms add together, factors multiply. So, hence the use of the word E for expression, T for a little bit of meaning to the letter. Notice the recursion here. So an expression is a sequence. We can see we can replace this E with an E plus T, and we could replace that next one with an E plus T. And so what we can derive from just this is a series of terms that are added together. We haven't done the multiply yet. Are you with me? The next level down here, we say that a term can be either a term multiplied by a factor, or just a factor. Those are separate from each other. Okay, see where this is going, because it should be fairly intuitive when you get to the other, when we finish this out. And a factor can be a parenthesized expression, or I'll give it a couple of terminal variable names, and we'll give it one more. All right, so what will the strings look like here? What do we have? Hello, IJ. I see your video is on. IJ is our TA.
Oh, I think I was muted. Hey, AI, how are you?
Ah, there you are.
It's really class.
Yeah. All right. IJ is our TA and grader, so feel free to use her capabilities. She's been through this class with me a couple of times, so she'd be in good shape. There will be another homework assignment I was just going to end up assigning today here when I when we get done. So that'll be on our context-free languages chapter 2 started. About the, I think it's about the same size assignment as what you had for one. I'm the one grading the exams, by the way. I still working those up. I've got, I will get those released as well as I ended up with a bunch of exams, and I will make every effort to get yours finished up and posted by the end of the day tomorrow. All right, so back to our example. Think about what kind of expressions you can generate here. For example, the only way that the way to get to terminals, you can either have terminals are all going. Let's make some observations that you should be able to extract from this. A first observation is that we're trying to see if, I guess we can say, will this string be generated through this grammar? Is a reasonable question to ask. A reasonable answer would be, well, he put it up on the board there, and it kind of looks like that's where he's trying to lead us. So it's probably a pretty good guess that we can generate that from here. Some things to observe. What are the terminals that we can generate? Well, anytime we generate a plus sign, there's going to be an expression on one side of it and a term on the other. So there could be a series. We could see by the E here that we could have a series of plus signs generated with terms in between. Ultimately, if you look, that E is going to either be replaced by a plus sign, or an E with a plus sign and another term, or finally we're going to get rid of that E with a term, a T at the end of all this. So this will generate a series of elements with plus signs in between them. Okay. Then what is the T for terminal? Not terminal, term, a mathematical term. Terms can generate factors multiplied together. So in a similar way that expression is a series of terms added together, a term is a series of factors multiplied together. And so the multiplied terms, again, we're going to have factor. Ultimately, this is going to be factor times factor times factor times factor, however many we want. We could have 0 of them if we just directly went. The letter A could be generated by this, by simply going E goes to T, T goes to F, F goes to A, and we're done. So A by itself is a mathematical expression. Let's see. Let's do a derivation. So starting at E, we looked at derivations last time, and we said a derivation is one that we start with the start symbol, and I would have to mark it as such. Usually it's the first one that gets written down, or the first one at the top of the rules anyway. And often we use an S. In this case, I use the E for expression, F for factor, T for term. All right. Well, let's replace, let's just go, can we get a parenthesized expression? We can put parentheses around by substituting E goes to T, T goes to F, and F goes to parenthesized expression. Notice as we generate more, the parentheses are always going to be balanced. That's something that we could not do. This is not just for your information. That's the start. This is not regular. You cannot sustain these rules using simply a DFA. One way of telling that is nothing in a DFA will let you say, I need to see if I see an open parenthesis, then don't accept this string until I see a matching closed parenthesis. And they can be nested any level deep that I want. You just can't do that with a DFA. Okay, where does this go? Well, the open parenthesis, let's substitute. I'm only doing one correct, well, an unabbreviated, a full derivation, such as what you should be equipped to do, involves rewriting and only substituting one non-terminal at a time for each. In other words, only applying one rule on each step of the derivation. So I'm replacing the E with an E plus T, and the closed parenthesis stays there. So I just substitute this, went to E plus T. Let's substitute a T for the E. Let's substitute T to F. We have open parenthesis. And I'm going to continue down. Replace that F with A. Are you with me? Are you tracking how the derivation is going here? The T got replaced with an F. The F got replaced with one of the terminals, the A in this case. And I can't just substitute. How do I get a terminal over here? I have to replace the T with one of its right-hand sides, which is the F. So we get something like this. And so we generated the string A plus B in parentheses using this grammar. Okay. Any question of what was going on? In fact, I did something to be consistent, which was I gave you a leftmost derivation. Why is it leftmost? Because at each opportunity to replace a non-terminal, replace one of the variables with something, I took the leftmost one as the one to replace. So we started with E. That's our start symbol. We always every derivation, every full derivation is going to start with the start symbol. So you start with an E. There's only one option, so we replace the E with the T. Replace the T with the F. And the F is where the parenthesized expression would get put in. That resulted in the open left parenthesis and the closed right parenthesis, which we carried along then in throughout the derivation. So these things are a little unwieldy. That's the nature of it because we're dealing with text, basically strings of terminals and non-terminals that can be derived. So then I replaced this E with the E plus T, so I could get the plus sign in there. The next step, I always chose the leftmost non-terminal, the leftmost variable, leftmost capital letter. I always chose that as the one that I was going to substitute. So here I had E plus T. I replaced this E with a T. I replaced this T with the F, and everything else stays the same. When you do the replacement, you take one, you apply one rule, and you replace the non-terminal with one of the right-hand side rules. So just to make it clear, again, I'm using some shorthand to fit it all on the board. How many rules are represented right here? For F, there's a rule that says F goes to parenthesis E. There's a second rule, F goes to lowercase a, F goes to B, F goes to C, F goes to D. So there are actually 5, count them, 5 rules on this one line here. There are 2 rules here, there are 2 rules here. And just to shorten the vertical space, we can use the OR, vertical OR bar to write them more succinctly. Whew. I need to get a drink of water here in a minute, but continuing on, I replaced the leftmost non-terminal F with the A. Then I continued on, replacing the leftmost remaining non-terminal, the T, with the F, and finally the F was replaced with its terminal B. All right, the only other thing we should show in addition to this is the parse tree. And I can't wipe out my beautiful grammar here. I want to show the parse tree for A plus B. And that's going to show exactly what rule and what contents of each rule were applied here. Let's see, we haven't got any space over here, do we? No. We haven't got any space over here. Not really. Okay. Just make sure my result comes out to match this. I'm going to make this go away. So that was a leftmost derivation, and I'm going to give you the Parse tree. Parse tree is going to show which rules got applied at each step along the way. So it's kind of a different representation of where the derivation came from. It starts always, the root is the start symbol. But now we immediately replaced E with T and the T with F. So it's read from top to bottom. The F generated our left parenthesis and right parenthesis, and in between the E. Okay, that E was replaced with E. We'll bring down our plus sign, plus T. We then replace that E with a T, an F, and finally that F got replaced with our A. And this T into an F, and then to the B. And so our final result, open parenthesis A plus B close parenthesis, can be represented as well. This shows what rules were applied and where each of the elements came from. So one of the rule, every node, every element, member of the tree, every member of the tree is a non-terminal. Every internal node of the tree is a non-terminal. All the leaves are the terminals. And all the internal nodes of the tree are non-terminals. And so you can read across, there must be a rule that says F goes to E. All the children of a node of the tree, all of those children are the elements that make up the right-hand side of the rule. What else can we point out? So you can read off, there must be a rule here. E goes to E plus T. Sure enough, that's right here. There must be a rule that says E goes to T. Yep. T goes to F. Yep. And F goes to A. So each one of these, the connections here shows a path of rule selections. Anything else? We can see F goes to open parenthesis, E close parenthesis from the children of F there. So we make up the tree by applying a rule and then making the children of that non-terminal, that internal node, be the individual elements of that right-hand side of that rule. All right, take a 1 minute break for the water trough here. I shall return. All right. I know you guys are just kicking back. You got your Diet Coke or whatever other market placement you prefer. I got my little cup of water. Uh-oh. Yeah, thank you, Emily. What's a little scary is that you had something like that so readily available. Just kidding. That's cute. All right. So for my next act, let's derive then. Here's a little problem for you. Let's see if you can come up with the parse tree. See if you can come up with a parse tree for this expression that we started with here. Using this grammar, this is a good, let's see, am I understanding this? Let's see, I think I have one hint I can give you is that it's probably easiest to start building the parse tree and then see where that leads. Notice that this is building, the recursive part is to the left. And so the first thing, the rightmost thing that's going to pop out here is this, the way this comes out, the rightmost elements will come out kind of first on here, and it'll build back as you go. So what you can do is start with the leaves and work your way up the tree to see where things get derived. Austin has a question. Yes, sir.
Actually, is it okay if I unmute really quickly? Because it'd be faster.
Yeah, absolutely. Sure.
So once because you start off with E, once you loop around all the way to F to get to that E plus T, that new E you have, do you have to loop that one all the way back around to get that one to E plus T again?
Yes.
Okay.
Yep, it has to go through its rules, replace each step along the way. So it's a little, what's a nice term would be verbose.
And then is it the same thing with T where you have to go to F first, or can you go to T times F? Because I didn't understand that one.
Oh, okay. So The way that we can derive the times here means that we're going to have something that's going to look like we're going to have a t goes to t, the times, and the factor over here. Then we can take that factor to c, and this t then has to go to an f before it can go to the b, like so.
Thank you very much.
Good. Hopefully that clears it up. So the way to figure out the derivation here, this is really building a parse tree, or parsing. We would say we're parsing that string of characters to figure out where they came from, what the parse tree is for them. Oftentimes you've heard the term, when people are arguing, sometimes people say, something like, you're just trying to parse my words, or you're, and what they mean is you're, applying an unintended meaning to the words that that wasn't what I meant, is usually what they're saying when they use that term. And so in this case, we're parsing to find out how can I derive this string. So as I said, to get the plus signs are going to come from that top rule. And let's see if we can build that up here. So we've got the A plus C times B plus A. This is our final, our set of terminals. Let's see. That looks pretty close. To put it in the parse tree format, we know that A is going to come from an F. The F is going to come from a T. That plus sign is going to come from an E plus T. F is always going to precede that. And so the E plus T comes from there. So the children of this guy are the E plus T. The E leads to a T, leads to an F, leads to a C. Oops, and I think let's see. Yep, I actually took it down a backwards path here. Let me try this from here. Okay, so E led to the E plus T. And actually, to get here, this thing is the term, so we needed an F times an F Stay with me. Gotta back up my tree a little ways. We started with our E. Hang with me. And well, I drew this out for a different one. And I need to replace here we go. This E went to an E plus T. This E went to E plus T like so. There it is. So initially, it's easier to see on a piece of paper in front of you. We have this E went to the T that led down here plus an E this E had to generate a E plus T here, plus T. And then this T generated the T times F. This T went to F, B, and like so. So at each step along the way, we can see what was substituted where. Okay, so you'll have a derivation example in your homework coming up that I'll get assigned. Now the question that I'm sure you're asking is, so what kind of a machine will accept a context-free language? We said a DFA will not, or an NFA will not. And around page stay with me here. Page 111 is where we start learning about the pushdown automaton. So we can use this area. Context-free grammars are the representation of context-free languages, and they need a pushdown automaton for recognition, or a PDA. Well, how does a PDA differ from a NFA or a DFA? Well, first of all, our plain old PDA is presumed to be non-deterministic. That means it can, we'll use the sense of non-determinism that says it will automatically choose if a correct path exists, the PDA non-deterministically will find the right path to accept the string if it can be accepted, or if it is in the language. Okay, so it can recognize strings whether they are part of the language or not. The PDA is a 6 tuple, as shown on page 112. I'm sorry, 113. We have states like an NFA. We have an alphabet. We have a stack alphabet. Stack alphabet, because a PDA is going to have a stack to push down onto. And that's a capital gamma. It's going to have a delta function, for transitions, a start state, and accept states. Okay, so it's going to look similar to our DFA and NFA, but here's the trick. If there's no move, then there's no move, and it would try to find an alternative path. What it does have on each transition, it has also a stack manipulation. So a transition, if you wanted to look on page 115, I guess, shows an example. So the tricky part on these a transition consists of a the alphabet symbol telling it when to transition. So it's going, from some QA to QB. So it's got the symbol that you're familiar with. Then it has a comma. And it says if the top symbol, it can take the form of trying to pick one out of the example that they're showing here. If the top of stack matches this symbol, then replace it, little arrow, with new symbol. And most often, you're replacing something it's currently on top of the stack, you're popping it off by replacing it with empty string. And you could alternatively, if you don't care what the top of the symbol, the top of the stack is, you can just replace it with, you could have something like, if it's an empty string, replace it with a 0. So we can effectively pop and push items onto the stack with the transitions. So this is just the introduction to the PDA. We'll cover it in more detail next time, but basically you've got your little control box. It's got state machine in here. And then it also has a stack onto which, so it's got memory. But it's memory that can only be accessed as a stack. Remember, a stack is an abstract data type, and a stack does not allow you random access. A stack only allows sequential access. And remember, it is last in is last in, first out. So the example that almost every book uses is something like cafeteria plates, where you can, when you add plates to the top, the stack pushes down. When you take things off, the next one pops up. And so the only access to the stack is via the top. You can add stuff into the stack, but to get the fourth thing down, you'd have to pop off the three things that are above it to get at the fourth one. So it does not have random access, and it requires you to pull off items in the opposite order of which you added them. All right, so questions in your mind might be, so that's all nice, but how do we use it? What do we do with it? Well, if you look, we'll go over the example on page 113, 115 next time. You should read ahead on that between pages like 112 and 115. Read ahead to get the understanding of how the push-down automaton works. It is different in that it accepts, there's 3 conditions for acceptance, and we'll finish with that. PDA needs to accept 3 conditions. The input string is used up. That means all the characters have been read and transitions have been made. It's gone through the entire input string, so there's nothing left over. Similar to a non-deterministic automaton, it cannot accept unless you've looked at all the characters. So input string used up, we get to an accept state. We reached the accept state, and the final thing is that the stack is empty. So those are 3 criteria that you want to, and I will definitely ask you about that on the upcoming exam. What are the conditions? You should be familiar with how does a PDA accept? Well, the first 2 makes total sense. It has to go through the input in order to accept a string. If it didn't get all the way through the input, then it certainly can't accept. Then if it got through the string, but it's not in an accept state, then, well, it didn't accept. But now if it got the string used up for the inputs used up, it got to an accept state, and the third thing that it has to have is the stack has to be left empty at the end. And so we'll see how that works, but most often there's a final step that takes you to the accept state, and at the same time empties the last items on the stack. All right, we will call it a night here. Working the excuse me, little cough. Not drinking enough water. I will work on your exams and get those posted by tomorrow. Thanks for your patience.